time for more practice. You can always use more practice, right? And the more we practice, the better we're going to get, the more confident we're going to feel. And we're going to walk into that exam head high saying, you can't scare me. I've seen it all. And you're going to do great. And we want you to do great. Make sure that you've got your table of Laplace transforms handy. More importantly, make sure you know how to use the table of Laplace transforms. Because you're not going to use everything, but you're going to use something. So you want to make sure you get that nailed down. All right, well, you got 6 problems. And just like on the test, right? The test will have 6 problems. And so we should practice. And so let's begin. First problem. Consider x double prime plus pt of x prime plus q of x equals f of t. So in other words, this says it's a non-homogeneous. And it says if you have 2 solutions, x1 of t, x2 of t to the homogeneous part, then a particular solution has the form xp is u1 of t, x1 of t plus u2 of t, x2 of t, where the functions satisfy the following system of equations. There's no question here. This is just explaining the process to us. And we're like, well, hey, wait, this is like method of variation of parameters, right? It's exactly method of variation of parameters. And, you know, there's sort of 2 ways to approach the method of variation of parameters. One is there's this long formula. And then one is to say, oh, you have a system of equations. We can solve the system for u1 prime and u2 prime, for which we can recover xp. All right. So this is just a reminder, a refresher to tell us, hey, don't forget, you've got this wonderful idea called variation of parameters. So we're given that we have our complementary solution, or if you like the homogeneous part, looks like c1 times cosine, c2 times sine. And our differential equation, x double prime plus x equals secant tangent. Problem is, find a particular solution. All right, good. Well, the nice thing is, they gave us a lot. You know, we didn't have to memorize the formula. Nice people. Nice people. These test writers are, you know, the nicest people. We also have some other things. We have the c1 times cosine and c2 times sine. So what's really happening here, these 2 pieces are our complementary solutions. So we should think of this as our x1 and as our x2. And we say, all right, well, according to this, what we'll have, and we're going to come into here, the only other thing, of course, that we'll really need here is that this part is our f of t. So we have u1 prime times cosine plus u2 prime times sine equals 0, and u1 prime times the derivative of cosine, all right, negative sine, and u2 prime times the derivative of sine, which is cosine, equals secant tangent. All right, and now it says we've got to find a particular solution, xp. And the instructions here, we don't have to follow the instructions, but, you know, they gave it to us. Probably it's useful to follow the instructions. And it says, hey, you have this system, and you can get u1 prime and u2 prime. And the way we can do that is Cramer's rule. And so, in particular, suppose we were solving for u1 prime. Well, what we can do, let's start up here. u1 prime, it's a ratio of 2 determinants. Now the downstairs, you take the coefficients. So cosine t, sine t, minus sine t, and cosine t. And upstairs, what we do is you say, it's going to be this, except the u1 prime, we're going to replace by the column. When I say the u1 prime, the column corresponding to u1 prime gets replaced by this part. So we're going to have 0, then secant tangent, then sine, and cosine. Okay, well, what do we have? Okay, so let's do the downstairs, because that's going to be nice. Cosine squared, subtract minus sine squared. It's cosine squared plus sine squared. And we'll write it down. But we know cosine squared plus sine squared, 1. Beautiful. Mwah. Magnifique. All right, upstairs, 0. Subtract. Then we have secant t, tangent t, sine t. All right, that's a lot of stuff there. But if we think about what's going on, secant is 1 over cosine, and then times by sine. Secant times sine is really tangent, so we have a tangent squared. All right, great. Beautiful expression. Now, a couple things. We already said the denominator is 1. And we say, look, this is a derivative. And we say, well, tangent squared doesn't really work for us like a derivative does. But we know there's a beautiful identities because there's trig involved. There's always a beautiful identity whenever there's trig involved. One could say trig is beautiful. It is. What's the trig identity that we'd like? Well, the trig identity that we have that's really nice with tangent squared, it says, hey, tangent squared and secant squared are essentially interchangeable. If you have one, you can really replace it with the other. And the identity in particular says the following. Tangent squared plus 1 equals secant squared. So if we have minus tangent squared, well, we can replace that by 1 minus secant squared, right? So we move the secant squared across, move the tangent squared across. All right, well, that's u1 prime. And now we say, hey, we can integrate that. So u1, if we integrate, would be t, and the integral of secant is tangent. So t minus tangent t. Okay, so that's our u1 prime. All right, well, now we'll switch and we'll do u2 prime. All right, what is that? Well, similar setup. The only thing that happens is now we're going to use the 0 secant t tangent t and replace the part that corresponds to u2 prime. So we're going to get cosine t and minus sine t, and then 0 and secant t tangent t. And downstairs, it's the same part as here, which we already know is 1. Now, do our multiplication. Well, cosine times secant. Cosine, 1 over cosine, they cancel, so we're left with tangent of t, and then we subtract 0, so it's tangent of t. And now we say, great, that's u2 prime. Well, do we know the integral of tangent? We do, because it's one of our 10 integrals that we know by heart. And you're probably thinking, oh, I know hundreds. You just need 10. There's 10 nice core integrals. And so in particular, the integral of tangent, we can say, is log of secant. All right, so great. So now we know what u1 and u2 are, and therefore we can come back here and say that a particular solution is the following. So our xp will be, and just read off, it's u1 times x1, right? So u1, t minus tangent t, times our x1, which is cosine of t, and then plus our u2, natural log of secant, times our x2, and our x2 is sine. And there we go. That is a correct answer. Now you might say, you phrased that a weird way, Steve. That is a correct answer. Is there a more correct answer? Well, no, correct answer is correct. I mean, that's the word correct. But there is an interesting thing that happens. Let's just note something here. If you multiply this through, you get t times cosine t. All right, that's no surprise there. Tangent times cosine. What is that? Well, tangent times cosine, the cosines cancel because tangent sine over cosine you get sine. Where else does sine show up? It's part of our homogeneous solution. So this is correct. Another correct answer we could say is, well, since cosine times tangent is part of the homogeneous solution, we can just absorb that into the homogeneous part of the solution. In other words, it's really redundant for the particular solution. So we could say it's t cosine t plus the natural log of secant t times sine of t. And there's another one. So these are both correct. So two beautiful answers. What a great problem. A nice way to start, right? It's a lovely, lovely way to start. Okay, so that's one down. So keep moving forward. Number 2. Okay. And, what do we have here? Oh, something a little different. And we have x prime, and it's equal to a matrix times x. But now the matrix isn't just constants. There's also functions of t. In other words, this has the form x prime equals a of t times x. Now, we've been dealing a lot with the notion, oh, what about x prime equals ax, where a is a matrix of constants. But there's nothing in the differential equations that says, oh, we can't have the coefficients varying as well. It's a lot harder to do. And so we say, okay, well, all right, that's fine. A lot of the same theories translate. Now the techniques, eigenvalues, out the window. But the ideas translate. And so what are we looking for? Well, there's part A and part B. Now show that we have x1 equals this and x equals that are both solutions. Okay, so let's start with that. So we'll start part A, and there's two functions, so we'll have to do them both. So let's look at x1. So we're going to look at x1 prime, and that says take the derivative. Now the way we take a derivative is just derivative of each entry. So we'll have to do product rule, so that's sine of t squared, derivative of the first times the second, plus, and now here, the first times the derivative of the second. Now when you take the derivative of sine, you get cosine, and so you're going to get a cosine of t squared, but then you multiply by the derivative of the inside, so that's 2t. There's already a t there, so put them together, you get 2t squared. All right, so that's the derivative of the first part. Derivative of the second part, well, okay, cosine t squared, because derivative of t is 1. Derivative of cosine is negative sine, so minus sine of t squared. Derivative of the inside is 2t. There's already t there, so that makes 2t squared. Okay, on the other hand, suppose we do t to the minus 1, 2t minus 2t, t to the minus 1, times t sine t squared, t cosine t squared. And what do we get? Well, t times t to the minus 1 would make this sine t squared. Then 2t times t cosine t squared would make 2t squared cosine t squared. Here we have minus 2t squared sine of t squared. Then t minus 1 times t will just be 1 and cosine of t squared. And now we do our great do these match, and well, other than changing the order, yeah, they match, and it's okay to change order. And so these match, and really the key is if they match, it means it's a solution. Okay, so we verified one. Got to do the second one as well. x2. So it's going to be very similar. We're going to have some very deja vu things because it's almost the same. What's different? Well, you've swapped the order and you've thrown a minus in there for some reason. Well, all right, well, other than that, no big surprises. So the root of the first would make this a minus cosine t squared. And then derivative of cosine is negative sign, but see how that we have a negative? So that makes this a positive, and then we'll have a sine t squared. Chain rule says multiply by 2t. There's already a t, so that's 2t squared. Downstairs, root of t sine t squared. Well, root of the first, 1, so we have sine of t squared. And the derivative of sine is positive cosine. And then chain rule means multiply by 2t. 2t times 2, 2t squared. All right. Now, that's x prime. So we have to check both sides. What we're really asking is, do these match? When we say they match, that means this equals that. So that's how we know it's a solution. So we've got to go through and do our multiplication. So we have our matrix, and we multiply by our x2 minus t cosine t squared and t sine of t squared. All right, multiply t to the minus 1. Okay, so that's minus cosine t squared. All right, and here plus 2t squared sine of t squared. That's good. Come down to the next one, minus 2t squared. Actually, minus makes a plus 2t squared cosine t squared. And then here, t and t minus 1 plus sine of t squared. And now, again, we play our matching game. Okay, match, good. Match and match, good. Everything matches. And so, yeah, all right, 2 for 2. Now, in some sense, the verifying, there's not really a lot you have to do. But you do actually have to carry out the computations. It should be very methodical. What happens when you take the derivative? What happens when you carry out the matrix multiplication? Do they match? And if the answer is yes, life is good. It's a solution. So that's how we do part A, show that something is a solution. Okay, so now we're ready to do part B, which says, hey, there's this idea called the Wronskian. And so we're going to compute the Wronskian. And the Wronskian is actually really clean when we're doing it for these problems. What happens? Well, what it is that with the Wronskian of our functions, there's really not any derivatives involved. It just says put them in. So we're going to put them in. The first column is x1. So we'll have t sine of t squared, t cosine t squared. The second column is x2 minus t cosine t squared and positive t sine of t squared. All right, so take the determinant. Doom, doom. So we'll have t squared sine squared of t squared, subtract a minus, so it really becomes a plus, t squared cosine squared of t squared. And you might think, well, hey, there's a t squared common. We can pull that out, and we can, so we will. And now we have something that looks familiar. Sine squared plus cosine squared. Like, sine squared plus cosine squared, we know that. But wait, there's a t squared on the inside. So how does that change the answer? And it doesn't. Okay, so sine squared plus cosine squared, as long as the insides are the same, regardless of what the inside looks like, is 1. So 1. So we say, aha, that means our final answer, the Wronskian, is t squared. Which is good, because that's not 0. It's not, when we say it's not 0, it's not the 0 function. And so it means our solutions are 2 linearly independent solutions. There's a problem at time 0. Well, of course, at time 0, they're both 0. So you definitely have some challenges. But as long as you're not at time 0, you can always solve. So, hey, this is a wonderful set of solutions to the problem. And in some sense, we're not surprised that time 0 breaks down, right? look at that t to the minus 1. At time 0, that's blowing up. So beautiful problem. And it says, hey, remember, differential equations, there's a lot more you can do. A whole new world out there waiting to explore. All right, well, that's number 2. Good. Well, let's keep going forward. And we'll write it. The next one, number 3. So write the ODE system. So whenever we see ODE, it's just a shorthand for differential equation. So differential equation system, x1 prime equals 4x1 plus x2, x2 prime equals 6x1 minus x2, in the form x prime equals ax. Also use the eigenvalue method to find a general solution of the system. So what are we doing here? Well, let's first just write them in a nice way right on top of each other. So x1 prime equals 4x1 plus x2, and x2 prime equals 6x1 minus x2. Well, this is going to become the left-hand side, those are our derivatives. So that becomes our x prime. Here, what we see is this is a nice linear system with constant coefficients. And so we can write it in the form where we group our coefficients into a matrix. So 4, 4, 1, 6 minus 1. Now, if they were being mean, they would change the order of these, but we wouldn't fall for that trap. All right, 4, 1, 6 minus 1, x. All right, there we go. There's our first problem, right? It says write it in the form x prime equals ax. Okay, so that didn't take very long. Well, that's why they had to give us a second part. Use the eigenvalue method to find a general solution of the system. Okay, that one might take us a little bit longer. Maybe. Let's see. So what do? Well, the eigenvalue method says, okay, find the eigenvalues and find the eigenvectors and translate those into functions. So that's what we're going to do. So we'll start by saying, all right, we're going to take the determinant of lambda I minus a. So that's the determinant of lambda minus 4, minus 1, minus 6, lambda plus 1. And that would be lambda minus 4, lambda plus 1, minus 6 times minus 1. And if you multiply that out, that's lambda squared. And then you have a plus lambda minus 4 lambda is minus 3 lambda. And then you have a minus 4 and minus 6, so that's minus 10. And now we're like, okay, we should have nice roots. And you should anticipate that your roots are going to be nice and reasonable. That, things will factor, or even if they don't factor, even, you get complex roots. Even the complex roots won't be that complex. So in this case, what do we have? Well, what we have is this can be written as lambda minus 5 and lambda plus 2. And you can check. Lambda squared, good. 2 lambda minus 5 lambda, that's minus 3 lambda, and minus 10. And remember, we set that equal to 0. And so now we're like, aha, good. We know our eigenvalues. So our eigenvalues are going to be 5 and negative 2. All right. So now the next step is to say eigenvectors, because when we talk about the eigenvalue method, we also need the eigenvectors that go along with our eigenvalues. Well, how do we find those? Well, we set up our matrices. So let's start with lambda equals 5 and see what we get. So you can put in here, that would be, we have 1, 5 minus 4, minus 1, and minus 6, and 6. So that's lambda I minus a. And I like to do this by thinking about this in terms of augmented matrices. For 2 by 2, it's almost to the point where you can kind of guess. And you'll see right away, like, aha, you can knock out the second row using the first row. And if you think about what this is really saying here, what this is really corresponding to a linear equation. And in particular, if we're thinking about this in terms of a matrix, a vector, say AB, then the first column is our A column, and the second column is our B column. And what we have is that we need A minus B equals 0. That's the equation that we're seeing here. So A minus B equals 0, or that says A equals B. So that says, look, our vector has the form, we can write it as AA or A11. And so that's our eigenvector for 5. So it's 1, 1. Now, can we check it? Yeah, we can do it really quickly, right? Imagine taking this vector, multiplying by the matrix. So, 4 plus 1, 5. 6 minus 1, 5. Aha, it works, right? Because that's 5 times what we started with. Great. Now, what else can we do? Well, the next thing we should do is a similar thing, but for our other eigenvalue. So for lambda equals minus 2. All right, what do we get there? Well, okay, so we're going to get minus 6, minus 1, minus 6, and minus 1. So, right, that's our lambda I minus A. And then we have our augmented matrix 0, 0. But same process as what we just did. Again, we see, look, it's redundant. They're the same, so we can knock one out. And we have our A and our B. And so what do we have? Well, minus 6A minus B equals 0. Or we could say, look, B equals minus 6 times A. So that tells us that our vector, which should look like A times B, really has to have the form A minus 6A, because I can replace B by minus 6A, or it's some multiple of 1 minus 6. All right, so that says this should be 1 and negative 6. Now, you can check it. Again, there's lots of checks here. I mean, I shouldn't have quite jumped in. I should point out, suppose you want to check, hey, did I get the right eigenvalues? One quick check you can say is, what do I get when I add? I get 3. Well, what do I get when I add on the diagonal? I get 3. They need to match. What's the determinant? Well, minus 4, minus 6, minus 10. What do I get when I multiply? Minus 10. Again, they should match. So there's ways to check that I get the right eigenvalues. And similarly, there's ways to check that I get the right eigenvector, right? You imagine multiplying. So if I multiplied here by 1 minus 6, you'd get 4. Minus 6 is minus 2. Okay, that's minus 2 times 1 is minus 2. Downstairs, what would we... All right, so we just did across and down. Second row, 6 plus 6 is 12. Well, that's minus 6 times minus 2 is 12. So, yep, that's the right eigenvector. So what does all this mean? Well, once you have the eigenvalue and you have the eigenvector, then you can say your general solution looks like x equals some constant c, and then you do e to the eigenvalue t eigenvector plus some other constant d, e to the eigenvalue, so minus 2t eigenvector. And that's your general solution. So once you have these pairs, the eigenvalue slips in up here inside the exponent, and eigenvector comes in. And especially when they're real and distinct, and you got all your eigenvectors, life is pretty straightforward. If you get complex, things get a little bit more interesting, but not too much. If you have repeated eigenvalues and missing eigenvectors, things get really interesting, but that's not this problem. All right, so yeah, that's it. We're done. And we're halfway through. Woohoo! Halfway. Well, that means we still got half the problems to go. Yay! More stuff. So, number 4. Find the matrix A so that the following matrix is a fundamental matrix of the differential equation x prime equals ax. So the reason it's emphasizing the word a fundamental matrix is that there's many of them. You can scale eigenvectors and you still have fundamental matrices. So in other words, if I doubled the column here, tripled that column, or if I swap the columns, or if you take some curious linear combinations. So these fundamental matrices are not unique. On the other hand, there are matrices that are fundamental matrices which essentially have a uniqueness attached to it. And you can see it here in the hint, e to the at. So anyways, what's the problem here? What's going on here is it says, here's a solution. What was the problem? What? We got to go backwards? Okay, so that's interesting. So we know what the solutions are. How can we recover what the original problem was? So our goal is we have to find A. And the hint says there are many ways to do this. So that's great, but that doesn't mean we know them all. We need to do things that we can do. So let's see if maybe the hint has more to say. And one approach is first find e to the at, and then say, what is the derivative of e to the at? Let's go ahead and do this just for fun and see where we end up. Now, what's the relationship between e to the at and this phi of t? Well, what it is, if you take phi of t and you multiply by phi of 0 inverse, that's e to the at. So if you have a fundamental matrix, if you multiply it by phi of 0 inverse, it'll always sort of put it into just the right form. And regardless of what fundamental matrix you start with, when you run it through this process, you'll always get the same matrix out. All right, so, well, that's not so bad. Okay, so what do we need to do? Well, we have phi of 0, and plugging in zeros fairly straightforward. 4, 3, 3, 1. The reason I say it's fairly straightforward is that all the e to the zeros are just ones. So now we need to find the inverse of this. Now that you can memorize certain formulas for 2x2s, that works, that's perfectly fine. Or you can memorize a process, that works, that's perfectly fine. I'm more of a process person. It's not that one way is superior to the other. If you have a ironclad memory and just say, oh, I know the formula, great. And if you don't, well, run the process. Because the nice thing about the process is you'll get the right answer. Of course, the other thing is you have to remember the process. And how does that work? Well, the goal is you start with the matrix. They want to take the inverse of. Over here you put the identity matrix. So we call it augmented matrix. And we're going to make this left-hand side look like the identity. And so the way to do it, the way I like to think about doing is I'm going to go column by column. So I'm going to multiply, say, the first row by a fourth, so I make a 1, because I want to make it look like 1, 0. So we'd have 1, 3/4, 1/4, 0, and we haven't done anything down here yet. Now subtract -3 times the first row to get to the second row, and well, 1, 3/4, 1/4, 0. Again, we haven't done anything to the first row. Then we have 0. Okay, now we have to actually start thinking. -9/4 plus 1. Well, -9/4 plus 1, that's 4/4. So that's -5/4. Then -3/4 and 1. Okay, so now our first column it's looking great. It matches the first column here. So move to the second column. All right, so I'm going to make this a 1. So multiply through by -4/5. And, well, we haven't done anything to the first row of this stage. So that we just copy. And second row will be 0 and 1, because -4/5 times -5/4 is 1. Then here, well, what do we have? Well, the negatives cancel, the 4's cancel. We'll get 3 fifths. And then negative 4 fifths. All right. And finally, we're going to come up here and get cancellation. So we're going to multiply by negative 3 fourths. Okay. And if we do that, well, we're going to get 1, 0, 0, 1. Good. Here, we'll get 3 fifths, negative 4 fifths. And the second part's not too bad, right? Negative makes positive. The 4's cancel. So it's really going to become 3 fifths up here. And the other part, we'll do it carefully. So minus 3/4 times 3 fifths is minus 9 over 20. Then we're going to add it to 1/4. Now 1/4 is the same as 5/20. So 5 over 20. And now if you put those together, we get negative 4 over 20. And that's negative 1 over 5. So you get negative 1/5. Now, what does all of this tell us? This part right here, let me use a different color. This is the inverse matrix that we're after. So, our punchline here is we have the following. So, phi 0 inverse, well, everything has a 1/5, so let's go ahead and pull that out. And then we'll have minus 1, 3, 3, minus 4. All right. Now, could we check to make sure we didn't make any terrible mistakes? Well, yeah. Multiply together. So, minus 4 plus 9 is 5. Multiplied by a fifth is 1. 12 minus 12 is 0. Minus 3 plus 3 is 0. 9 minus 4 is 5 times a fifth is 1. So it's the inverse. So now we're like, woohoo, we've got our phi 0 inverse. So next step, we're going to multiply phi of t by phi 0 inverse. So we're going to get the following. All right, so e to the at is 4e to the 3t, 3e to the minus 2t, 3e to the 3t, e to the minus 2t, times 1/5 minus 1, 3, 3, 4. All right, well, let's see what is going to happen here. So we're going to get minus, well, the 1/5 we can leave in the front. 1/5, then we're going to get minus 4 e to the 3t plus 9 e to the minus 2t. Then we're going to get 12 e to the 3t, and, oops, I forgot to copy a minus sign here, and minus 12 e to the minus 2t, and then next row, minus 3 e to the 3t plus 3 e to the minus 2t, 9 e to the 3t, and minus 4 e to the minus 2t. All right, we've done it. We found e to the at. And then there's this mysterious question. What is the derivative of e to the at? Well, that's actually, we talked about that. That's a e to the at. Now, why do we care? Plug in t equals 0. So at t equals 0, this goes to the identity matrix. So the clue here is, oh, if I take a derivative and then I plug in 0, the result will be a. So the derivative of e to the at, well, that's 1/5. And then we have minus 12 e to the 3t, minus 18 e to the minus 2t. Here it'll be 36 e to the 3t, plus 24 e to the minus 2t. Down here, minus 9 e to the 3t, minus 6 e to the minus 2t, 27 e to the 3t, plus 8 e to the minus 2t. Okay, plugging in 0. So that's the next thing we're going to do. We'll plug in 0, and we'll see what happens. And so what do we have? Minus 12 minus 8, well, that's minus 30. And times a fifth. So at t equals 0, we get minus 30 times a fifth, minus 6. 36 plus 24, that's 60 times a fifth, 12. Minus 9 minus 6, that's minus 15 times a fifth, minus 3. 27 plus 8, that's 35 times a fifth, 7. And that's the answer. There we go. Wow, it works. We think. I hope that's true. Well, we don't just have to hope it's true. It actually is true. But you might be thinking, that was not the way I was thinking about it. Is there another way we could do this? You know what? Let's do it another way. Just to show you that, yeah, there are other ways. And hopefully we'll get the right answer. Well, at least let's hope we get the same answer. So grab some paper here and cover it up so we aren't tempted to look at the answer that we already have. And you might say, okay, so what's another way to approach this problem? Well, let's figure out what we can gain from phi, or, if you like, from phi. So we could say, hey, looking at this phi, I can think of this as e to the 3t 4, 3 as being the first column, and e to the minus 2t 3, 1 as the second column. So that's sort of, we stare at that, and we say, oh, this says, if we look at, because remember, these are coming from solutions, and these solutions come from eigenvalue, eigenvector pairs. So this says, oh, okay, so if you have an eigenvalue of 3, then the eigenvector looks like 4, 3. And then we can do the same thing here. Here, the eigenvalue is minus 2, and then the eigenvector would be 3, 1. And so we've got our eigenvalues and eigenvectors. Now, at this stage, there's sort of two ways to go. One way is to say, oh, there was this really cool fact that you might remember. And it says the following. It says if you have a matrix A, you can write it in the following way, where here you have your eigenvectors. And so what would that be? Well, in our case, it would be 4, 3, 3, 1. And then you have your 3 minus 2. So these are your eigenvalues on diagonal. And then over here, what would you have? Well, you'd have the 4, 3, 3 plus 1 inverse. So this is the inverse of your eigenvectors. We'll put that in quotes. All right, so you put your eigenvectors in, fill up the columns, put in your eigenvalues on the diagonal, and then here's the inverse of your eigenvectors. Now, we can actually check this because 4, 3, 3, 1 is what we did before. It's coincidence? No, there aren't any coincidences. Well, I hope not. Okay, so we know what that inverse looks like. So we're just going to copy here. So we have our 4, 3, 3, 1, our 3, 0, 0, minus 2. And here is our 1/5. And so I'm just going to copy here. And we would have our minus 1, 3, 3, and minus 4. And now you go through and carry out the matrix multiplication. And you say, okay, well, all right, so that would be what? 12 plus 0 makes 12. Here you have 0 minus 6. 9 plus 0 makes 9. Then you have 0 minus 2. And times it by the 1/5. Actually, we can put the 1/5 in the front. Just move the constant up. Minus 1, 3, 3, minus 4. And we say, okay, so that's really 1/5. And minus 12, minus 18. So that's minus 30. 36 plus 24 would be 60. Minus 9, minus 6, minus 15, and 27 plus 8 makes 35. And if you multiply the 1/5 through, you'll get minus 6, 12, minus 3, 7. And let's see, do we fit them? Where can we get them both on? Minus 6, 12, minus 3, 7. Minus 6, 12, minus 3, 7. Woohoo! Now you're like, Steve, I don't like this one either. You're like, in order for me to do it this way, I have to sort of remember this fact. And I know you said it in class, but what if I don't remember that? Okay, all right. So here's one more way you could do it, right? We said there were multiple ways. We're still going to get this information. That one, that's a fact you should be able to say, if I have phi, I can grab solutions. And now we say, okay, we're after A. So let's just write A as our A, B, C, D. And we've got eigenvectors, eigenvalues. So what does that mean? Well, that says, hey, the following should be true. If I take A, B, C, D times 4, 3, right? So I'm multiplying by my eigenvector. That should be equal to, well, scale 4, 3 by the eigenvalue, 12, 9. And by the same token, if we take A, B, C, D times 3, 1, that would be, scaling by -2, -6, -2. Okay, so what does this give us? Well, we have 4A plus 3B equals 12. So 4A plus 3B equals 12. And here, we'll get 4C plus 3D equals 9. Over here, A times 3 plus B equals -6. And 3C plus D equals -2. And we now have 4 equations and 4 unknowns. And we just work our way through it. So we really can split into 2 parts. You can say, hey, check this out. 4A plus 3B equals 12. 3A plus B equals -6. So let's do the following. Let's multiply the bottom row by -3, and we'll add. 4A minus 9A makes -5A. 3B minus 3B is 0. 12, and then plus 18 makes 30, which says A should be -6. Okay, so now that you know A, throw it back up here. So we can come to our conclusion that 3 times negative 6, which is minus 18, plus b equals minus 6. So that says b, add 18 to both sides, is 12. All right, so now we know our a, b. So negative 6, 12. C, D, run the same process. So we have 4c plus 3d equals 9. 3c plus d equals negative 2. So same process, multiply here by negative 3 and add. What will we get? Well, we'll get minus 5c, 0d, and here 9 plus 6 makes 15. Okay, so c is negative 3. Negative 3. And now, well, minus 9, right? That's 3c minus 9 plus d equals minus 2. So that says d has to be 7. So d is 7. And there we go. So no fancy matrix multiplication, just saying, okay, we know eigenvalues and eigenvectors, and that forces relationships on it. And does that work? Yeah, they match. The answers match. Well, of course they match. There's one answer. So regardless of how you approach the problem, you're always going to get the same answer out. So that just shows you there's lots and lots of ways to get there. Isn't that cool? Isn't it great that we have more than one option? Math is so beautiful. All right, I hope you're enjoying that. We still have 2 problems left. It feels like we just did like 5 problems in a row on that one problem. So, all right, let's do a cool down. All right. So, given the following system of differential equations, so we have x double prime plus 3x prime minus 2y prime equals t squared sine t. X double prime plus x minus 5y equals 0. And we have x of 0 equals x prime of 0 equals y of 0. All right, good. Find y of s. So in other words, the Laplace transform of y of t. And the answer should not contain x of s. All right. Cool. So, good news, we do not have to solve for y of t. Whew. All right. That's probably some great news. So this feels like, where we have a system of equations, and so it feels kind of like a method of elimination. In essence, you could do this in 2 ways. You could run method of elimination and then apply Laplace transform, and then you get the answer. Or you say, hey, let's apply the Laplace transform, and then we'll do what we do in method of elimination, which is like a Cramer's rule type thing. Either way, it's really the same result. And because method of elimination is essentially a Cramer's rule in play. So the question is, do we do Cramer's rule first or Laplace transform first? So here, let's do Laplace transform first because we need some practice. Don't we all need practice? I think so. I think that's a great thing. Okay, so where are we at? So we have, we're going to take the Laplace transform of x double prime plus 3 Laplace transform of x prime minus 2 Laplace transform of y prime equals the Laplace transform of t squared sine t. Okay, so this one's going to take us a while. Let's grab our table, right? We've had our table waiting for us to pull out. We know how to handle x double prime. That's on our table. And because our initial conditions are all 0, it'll make it really easy. So the x0, x prime 0 goes away. Similarly, when we do x prime, that goes away. So the Laplace transform of x double prime is the s squared x of s. So we have s squared x of s. X prime will be, there's a 3 there, don't forget that, s x prime of s. And Laplace transform of y prime, well, it's like x prime, just x's become y's. Again, we still have 0 as our initial conditions. So minus 2s, There's no prime here. That's just a really thick parenthesis. Don't tell anybody. Shh. Minus 2s y of s. Okay, good. Now, Laplace transform of t squared sine t, and we look at our chart and say Laplace transform of t squared sine t is not on there. Whoops. Uh-oh. Can we do it? Well, yes, we can, right? Because the punchline is, not every single function you might ever encounter in your life is going to be on the table. But the idea is the table should give you enough to go off of. We have t sine t, so we can do that. We're just short 1t. And now we're like, oh, if you want to add a t, there's this rule here that says if you want to throw a t in front, it's minus the derivative. So we say, okay. So we're going to really combine these two rules. We know how to do t sine t, and we know how to add a t by doing a derivative. So what this will be, there will be a minus sign coming from that minus sign there. The derivative with respect to s of the t sine t, which I'm going to copy from there. So that would be 2 times s over s squared plus 1 squared. Okay, so let's actually carry that computation out. That would be, looks like a quotient rule, because it's a quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom. So 2 comes down, s squared plus 1 to the 1 times 2s. All of that over the bottom term squared. So we now to the 4th power. Well, but we can simplify. And we probably should, because we're still going to do stuff with it. The rule of thumb is if you're going to do more things, simplify. If it's the last thing, don't worry about it unless you have to. But we're doing more stuff. We haven't even gone to the halfway point of this problem. It's going to feel like we're past the halfway point pretty soon, but we still got to do some work here. All right, so let's be careful here. Notice how everything has an s squared plus 1. So I'm going to cancel off a single s squared plus 1, and that'll clean that up. And now, what do we have? Well, downstairs we have s squared plus 1 quantity cubed, which is perfectly fine. Here we'd have 2s squared plus 2. Don't forget the minus. All right, as minus 2s squared minus 2. So minus 2s squared minus 2. Minus minus makes a plus. 2s times 2 times 2s. So that's 8. So that would get us to 8s squared. Or, if you like, that would be 6s squared minus 2 divided by s squared plus 1 quantity cubed. Okay. Whew. Good. So that's the Laplace transform of t squared sine of t. Wow, that's nice. All right. Well, where to from here? Well, our next step is going to be, we have this other equation that we have to do. How is just one equation? And so let's do our other equation. Well, maybe we'll switch colors just to emphasize, hey, we're in our other equation here. So we're going to look at Laplace x double prime plus the Laplace of x minus 5 Laplace of y equals 0. Oh, there we go. We caught a break. So we have s squared x of s plus x of s minus 5 y of s equals 0. All right, because we're just doing the same thing that we did before. Now, if we gather things, we can really think about this as a nice system. So in particular, we can write this as s squared plus 3s times our x of s minus 2s, our y of s, and then we have our s squared plus 1 x of s and minus 5 y of s, and equals, on the first one, 6s squared minus 2 over s squared plus 1 cubed, and on the second one, 0. All right, and something that'll feel very familiar. What's going to happen next? Well, the answer will not surprise you. We have 2 equations and 2 unknowns. I mean, someday in the future, maybe they'll change this class names from differential equations to 2 equations, 2 unknowns equations, because you do a lot of that. But we know how to solve these. And in particular, we need to find y of s. And so we're in the home stretch. Say, hey, there's a way to do this by Cramer's rule. So y of s is going to be a ratio of 2 things. Downstairs are these coefficients. S squared plus 3s minus 2s, s squared plus 1, and minus 5. Upstairs, we're going to have the same, except for the y's, we replace it by that expression. So s squared plus 3s, s squared plus 1, 6s squared minus 2 over s squared plus 1 cubed, and 0. The hardest part is just trying to squeeze it all in and still stay legible. The good news is upstairs, it's pretty quick to compute because you get 0 here, and here you get an s squared plus 1 to actually cancel. And don't forget there's subtracting that, so this would be 2 minus 6s squared divided by s squared plus 1 quantity squared. Because the s squared plus 1 cancel, and the reason the signs change is you subtract. And downstairs, well, okay, so minus 5 s squared plus 3s, let me be more careful here, minus 5 s squared and minus 15s, right, because I'm multiplying here. This direction will have a minus this, so plus 2s cubed plus 2s. Or, if you like, this becomes 2s cubed minus 5s squared and a minus 13s. The good news is we don't have to solve because this probably doesn't factor nicely. But we don't have to worry about it. Yes. Okay, so what's our final answer? Well, the thing is we can move this upstairs. And so our final answer, and I'll write up here just for space reasons, is we say that y of s will be 2 minus 6s squared over s squared plus 1 quantity squared times, if I wanted to, we could actually factor an s out. You don't need to, but I'll go ahead and do it just to make it look like I'm doing something fancy. S, and then we'll have 2s squared minus 5s minus 13. And there we are. That's it. That's the answer. So that's what y of s would become. And the good thing is you don't have to solve for y of t, so we don't have to take the inverse Laplace transform. What happened on this problem? This is one of those problems where it's like, okay, we've been doing it for so long, I kind of lost track of what was happening here. So can you just remind us? So there's a couple of important things that happened. So we took the Laplace of both equations. We had to use the fact that when we multiply by t, we take a derivative. So that's how we ended up doing this part was we had multiply by t, take a derivative. Don't forget the minus sign. So that's what happened here. And then we use Cramer's rule to say, oh, if we want to solve for y, we can do that. And so that's what was happening in this last part, was doing Cramer's rule. And then just a little bit of cleaning up at the end. And yeah, that was it. And life was good. All right, well, that was a good, challenging problem. One more. Let's hope this last one is a nice cool down, right? We're ready for a cool down type problem. So, last problem, number 6. Solve for x of t, where x double prime plus x prime is equal to 1 plus 2 u, and so this here u represents the on-off switch. It's the unit step function that turns on at time 2. And x of 0 equals 1, x prime of 0 equals 0. All right, well, let's see what happens. Now, you technically speaking don't have to do Laplace transforms for this because it doesn't tell you to, but you kind of want to do Laplace transforms because the only times we've talked about using things like unit step function is in Laplace transforms. But the other way to do this is to say, oh, let me do 2 differential equation problems. You know, one that handles before time 2 and one that handles after time 2, and glue them together. But that's twice as much work. We'd rather just do it once and be done. And that's the power of Laplace transforms. One and done. All right, so we begin. So we're going to say, all right, take Laplace transform both sides. So Laplace transform of x double prime plus Laplace transform of x prime is the Laplace transform of 1 plus 2 times the Laplace transform of u t minus 2. Okay. And now we start grabbing our handy-dandy guide. X double prime, we can handle that. That's s squared x of s. X of 0 is 1, and x prime of 0 is 0. So we would have s squared x of s minus s, because we have x of 0 times 1, and the other term goes away. The Laplace transform of x prime will be s x of s and minus 1. Yep. Equals the Laplace transform of 1 over s, plus 2, the Laplace transform of u of t minus 2, well, that's e to the minus 2s over s. All right. So there we go. So now we start working the problem. We'll have s squared plus s times x of s, and we'll move the rest of it to the other side. That's s plus 1 plus 1 over s plus 2 e to the minus 2s over s. So group the x of s terms, move the non-x of s terms across. And now we divide. So x of s, and well, before we divide, let's just make some quick observations. This is really the same as s times s plus 1, because you can factor out. And notice how we have an s plus 1 right there. Perfect. And so, from the first piece, we'll have simply 1 over s. And then we have 1 over s squared times s plus 1. And then we're going to have 2. And I'll even pull off this e to the minus 2s. And then 1 over s squared times s plus 1. And now, you might say, hey, that's good to go, because it is. That's going to require partial fractions, because it will. And then you say, and that partial fractions is the same as that partial fraction, which means we only have to do partial fractions one time. All right, but we do have to do it. So let's do it. And all right, we'll grab a new color here. So, some work. We're going to say 1 over s squared times s plus 1 is something over s plus something over s squared. You got to work your way up, step by step. And then something over s plus 1. All right, well, clear your denominators, and what will you get? You will get that 1 is equal to a times s plus 1 plus b times s plus 1 plus c times s squared. And now make good choices. I always like to start by making good choices. For example, I'm involved with differential equations. Great choice, right? Absolutely. Absolutely. And but here, when we talk about good choices, just, nice values for s. Things that make terms vanish. We want zeros. So, easy candidate, 0. We'll get 1 equals 0 plus b plus 0. So it's like, okay, we found b. Great, b equals 1. That wasn't so bad. How about negative 1? Then we'll get 1 is 0 and 0 and c. So 1 equals c. Like, okay, 2 for 2. Beautiful. All right, well, how do we get our last one? The problem is there's nothing else to make things 0. But on the other hand, we now know that b is 1, and we know that c is 1. So just pick a number. Let's say positive 1. Okay, why not? Positive 1 seems like a reasonable number for us to pick. And what will we see? Well, we'll see that 1 is equal to 1 times 2, which is 2a. Here we'll get 1 times 2, which is plus 2. And here we'll get 1 times 1, which is 1. So, well, if we put it all together, we see, for example, we can cancel the 1s. 2a equals minus 2. And the conclusion is a equals minus 1. All right, so what we can now say is we go back to the previous part and we say, hey, this part is really 1 over s from there. And then we have our a, which is minus 1 over s, plus our b, 1 over s squared, plus our c, 1 over s plus 1. Okay, that's the piece there. And then we're going to have plus 2 e to the minus 2s. And then we just copy it again. Minus 1 over s plus 1 over s squared plus 1 over s plus 1. And we're in luck. We get some cancellations. And now we're ready to actually write down our answer, essentially. I don't think there's much else that we need to do till we get to that point. So what is x of t? So we go through 1 over s squared. Well, is that on our list? It's almost on our list. That would correspond to n equals 1, right? 1 factorial over s squared. So that is going to be t, so that we get t. S plus 1, well, s minus a, we can handle. So think of this as s minus minus 1. So that would be e to the minus t. Okay, so 1 over s squared became t. 1 over s plus 1 is e to the minus t. And then we have the 2. And then we have stuff here. Now, normally, this part right here, if we didn't have any other information, if we just saw that by itself, well, minus 1 over s would become minus 1. 1 over s squared would become plus t. And 1 over s plus 1 would be e to the minus t. Now, this part right here, the e to the minus 2s, is telling us to shift over by 2. So what's going to end up happening is we're going to take this expression and shift by 2. So we're going to get minus 1 plus, and then here, t minus 2, because we shift over by 2, plus e to the minus t minus 2. And then we need to turn on our switch. So we're going to get u of t minus 2. We can clean it up a little bit. At this stage, we're done. But our little bit is, well, this minus 1 and that minus 2 can go together. So why not? Let's go ahead and do that. So plus 2, t minus 3 plus e. And upstairs, we can write this as 2 minus t and u t minus 2. And that's it. We're done. Ah, wow. What a fun problem. Well, of course, they're all fun. They've all been fun problems. Isn't it great? And I hope you've enjoyed these, and hope you keep studying. That test is coming. We want you to do well. All right. See you later.